One final aromatic mechanism that we want to discuss is called elimination addition. So it's different from nucleophilic aromatic substitution, and it's different from electrophilic aromatic substitution. In this case, we can see that we have a ring with just a leaving group attached to it. We attack it with strong base, strong nucleophile, sodium hydroxide in this case, and the end result is that we've replaced the leaving group with our nucleophile. We can do that with sodium amide as well, and we replace the leaving group with the NH2 group. What becomes interesting about this mechanism is when we have a substituent attached to it. Here we have methylchlorobenzene, or chlorotoluene, and let's use the same Na sodium amide, I should say. And let's explore the products. We'd expect to get this product, but what we don't expect is that we also form this product. So that's interesting, and that's actually in a 50-50 mixture. So what's up with that? How do we get these two regioisomers now? Because we have the methyl group there. Well, scientists conducted a labeling experiment where they labeled the ipso carbon, the carbon that's bearing the leaving group. And I'll label my ipso carbon with a red dot. The scientists used a carbon-14 atom in that position, and so you can sort of track where that carbon ends up. So let's take our labeled chlorobenzene. We're going to treat it with the same sodium amide in ammonia, and we're going to get the chlorine. I'm sorry, this is not a chlorine, this is a sodium, or an amide. Let's erase this. And we're going to get that added to the same carbon that the chlorine was on, but we're also going to find that it's added to the adjacent carbon. So our labeled carbon is either attached to the new nucleophile, or it's attached, it's next to the new nucleophile. And this is a 50-50 ratio as well. So this led scientists to propose an interesting mechanism. So let's look at chlorobenzene, and we'll put the methyl group on here so we can keep track of maybe different regioisomers. And we have hydroxide ion. We have lots of heat. Remember, on the previous slide I showed you 350 degrees Celsius. So what's going to happen here is that we remove the H, and we essentially do an E2 elimination. This is E2-like. I'm going to say like because we don't really do E2 eliminations where we have vinyl carbons or sp2 hybridized carbons. But the result is this molecule, and that's poorly drawn. Let me try that again. This is called benzyne. It's like an alkyne, but in a ring. So as you'd expect, if you've been in my class before, you'll know that I really like to point out that these carbons are sp hybridized, and generally they're linear, right? When we draw alkynes, they should be a linear carbon, and this ring is obviously not linear. So this alkyne is under a great deal of strain, and it's highly reactive, and we would expect it to react immediately with another ion of hydroxide, and it could attack this way, or it could attack via the green pathway on the other side of the triple bond. And then, of course, both of these can be protonated by water or anything else, any other source of hydrogen that's present. Probably going to be water because we formed water in the first step. And we get the neutral compound there. And if I use water here, you can draw this proton transfer step, of course. And you can see that I've created the two different regioisomers here because I had two different places to attack on the benzyne. And these two carbons are different because my ring is now unsymmetrical because of the presence of this methyl group. If there is no methyl group, both of these carbons are identical. We get one phenol that's produced. We don't get regioisomers. So when we have a substituent in addition to the leaving group on the ring, we get a mixture of regioisomers. So this reaction is less useful if we have a di or tri-substituted aromatic ring that could potentially lead to a number of regioisomers. Scientists have proven that benzyne exists by reacting it with other molecules that like to react with multiple bonds or with triple bonds. So we'll see maybe some more hints of that in a later chapter. But this is elimination addition. And you'll notice the order that we say that word is important. We do the elimination first, then we do the addition. And that allows us to put an OH or an NH2 group on a ring that bears generally a chlorine or a bromine.